the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is a fifth and final video in a series on the least squares problems from linear algebra. This is for students who are going through the orthogonality topics and least squares topics in their linear algebra course. And as it is the final video in this series, it is assumed that you know or have seen all the stuff concerning least squares problems, solutions via normal equations, the uniqueness of least squares solutions, and orthogonality and solutions to least squares problems. Now we're going to dip our toes into QR factorization and solutions to least squares problems. And we'll do this by stepping into this theorem right here. Given a matrix, doesn't have to be square. Actually, in fact, all the matrices we've been talking about in this entire video series need not be square matrices. So, given a matrix, could be square or not, with linearly independent columns, that is going to be very important because that gives us a lot of power. Remember, if you have linearly independent columns for your matrix A, then you're guaranteed to have a unique solution to the least squares problem. It is also the case that A transpose times A is going to be invertible. However, again, given a matrix A with linearly independent columns, we're going to let A equal QR be the QR factorization of that matrix A. And remember, you use the Gram-Schmidt process to go ahead and find the QR factorization for a matrix A. We will do it in a moment anyway, so if you need a review, we're going to be doing it here. Then it will be the case that for each vector B in Rm, the equation Ax equals B has a unique least squares solution that we already knew just because of the fact that A has linearly independent columns. However, what we didn't know was that that solution can be found by computing R inverse times Q transpose times B. Remember, given the same exact conditions that A has linearly independent columns, we had that the least squares solution, this is from last video, is equal to the inverse of A transpose A times A transpose B. However, if you already have the QR factorization, or maybe you just want to do the QR factorization, you can also find that unique least squares solution by using the following formula. Again, which is R inverse Q transpose B. Now, before going in and actually proving this, we'll actually do it again like we have been doing lately at the end of the video. Let's go ahead and dive into an example to showcase how this is done. Find the least squares solution to Ax equals B, where A is this matrix right here and B is that vector right there. And we're going to do this using a QR factorization. Now remember, to do the QR factorization on a matrix A, basically what you're going to do is you're going to orthogonalize those column vectors in that matrix A, and then you're going to normalize them. To find R, you'll take that resulting matrix, we're going to call Q, you'll transpose it and multiply it by A. That will give us R. So let's go ahead and do that here. Remember how QR factorization works. The first thing you're going to do is choose one of these two vectors, and you're just going to call that vector Q1. Actually, that's what I'm going to call it in this case. So I chose Q1 to equal A sub 1. And now I'm going to let Q sub 2 equal A sub 2 minus the projection of A sub 2 onto the space spanned by Q sub 1. And that's how I'm going to denote it here. Again, Q sub 2 is just like our vector A sub 2, except we're going to remove or subtract from it the shadow of A sub 2 that's being cast onto the subspace generated by the vector Q sub 1. When you do that, you actually get a vector that's orthogonal to the projection of A sub 2 onto Q sub 1. That is, you get a vector that's orthogonal to Q sub 1. Which is really nice. That's exactly what you want. Doing the mathematics here. And I should pause for a moment because I mentioned when I was doing the Gram-Schmidt process and then the QR factorization process that it's a good idea to always write these vectors Q1 and Q2 dotted with themselves. So I'm going to go ahead and write the vector q1 dotted with itself off to the side. That's just going to be very important for us. What is that? 9 plus 16, that's 25. Now I'll go back to work here. That's a sub 2. Now let's take a sub 2, dot it with q sub 1. So that'll be, what is it, negative 18 minus 32 plus 0. We're going to divide that by q1 dotted with itself, which we already have written in red up above, and multiply that result by, oops, I didn't even write it. I should have written it. Sorry about that. Q sub 1. Little minor hiccup there. Sorry about that. But let's go ahead and clean this up. Well, that's a spectacular vector. I'm going to go ahead and quickly write down what q2 is dotted with itself. This is q2 right here, 0, 0, 1. And by the way, you could double check very quickly that q1 dotted with q2 is going to be 0. So therefore, these two vectors are orthogonal. And we are done finding q, almost. What we have to do at this point is actually take those vectors and normalize them. And I'll do this in a blue ink, because remember, q itself, the columns are going to be orthonormal, not just orthogonal, but orthonormal. So we want to normalize these vectors q1 and q2. q2 is actually normalized already, but q1 I'll go ahead and normalize right now. Remember, the norm of q sub 1 is actually the square root of the dot product of q1 with itself. So it's going to be the square root of 25. So we have 1/5 q sub 1. Oh, and by the way, the notation I use, this is the normalized version of the vector q sub 1. And I could also write the normalized version of the vector q sub 2 is actually q sub 2 itself. All right, so there's our normalized versions of those vectors. Let's go ahead and make q out of them. All right, that works out very nicely. So again, I know that A, the matrix A right there, is going to be the same thing as q times r. However, because q has orthonormal columns, q transpose times q is actually the identity matrix. So if I want to find r, I'll multiply both sides of that equation on the left by q transpose so that r is equal to q transpose times a. All right, so this gives us r right here. We have q and r ready to go. Now, what the heck did that theorem tell us? Let's go ahead and find out. Oh yeah, the least squares solution to ax equals b is going to be the inverse of r times q transpose times b. By the way, this is only true if those columns of A were linearly independent, which they were. So let's go ahead and use this. The nice thing about R inverse here is that it's going to be super easy. R is just a simple little 2x2 matrix, and computing its determinant, wow, R is always an upper triangular matrix with positive values along its main diagonal. So that's really going to be very nice. The inverse of R is going to equal 1 over 5 times 1, 10, 0, 5. Remember, take the determinant, so that would be 5, and then swap these two, so it's 1 and 5 instead of a 5 and a 1, and negate these two. And that gives us what we have right here. And then Q transpose we already have written, so let's go ahead and just rewrite that. And then times B. And B, where is that bad boy? Negative 172. Now I'd probably do the matrix vector multiplication right here first. It just seems easier, so let's go ahead and do that. That's perfect. Actually looks really nice. Now let's go ahead and do this matrix vector multiplication. I'm not going to take care of that 1/5 till the very end. I dislike having to deal with fractions, so I'll just leave that out front. And luckily, good thing I did, because you can see this cleans up very nicely. And there we have it. That's the least squares solution for AX equals B for that given A and that given B. Now I didn't even bother starting the problem to see if B was in the column space of A, but I'm going to pretty much guarantee it's not. You can double check right now. If you were to try to plug in 5, 2 against A here, so multiply column 1 by 5 and column 2 by 2, you will see that's going to be 15 minus 12, which is 3, which is not that. So immediately I know that B is not in the column space of A, because if it were in the column space of A, our least squares solution would actually have solved ax equals b as well. Now this all said and done, and this is the only example I have in this video, we're going to hop back and prove the theorem. So again, the theorem is just telling us if we have a matrix with linearly independent columns and we do a QR factorization, then we have a unique solution to the least squares problem, and that solution is R inverse Q transpose B. And the way we're going to prove this is actually we're going to start with R inverse Q transpose B. We're going to start with that idea. We're just going to let X hat be that. We're not saying that we're assuming that's a solution. We're just starting with, hey, what if X hat is equal to that? What does that mean? Well, then A times X hat is going to be A, which is QR, times X hat, right? Because A is QR. We're assuming we can do a QR factorization. Now X hat, remember, is R inverse Q transpose B, so I'll just trade that out. And you can see R and R inverse cancel, and we have Q times Q transpose B. However, Q from the QR factorization process has orthonormal columns. And that's important. Take a look at what I call Theorem 10, or actually my author, the author of this textbook, calls Theorem 10. It's the orthonormal decomposition theorem. If you have an orthonormal basis, in other words, if our columns of our matrix are orthonormal and you have a vector y in your space, then your matrix formed of those orthonormal columns times the transpose of itself times that vector y is equal to the projection of that vector y on the subspace generated by those orthonormal basis vectors. Now think about what we just did. We had Q times Q transpose times B. Well, that means that that's the projection of B onto the space spanned by the columns of Q. So we're going to use that right now. Q times Q transpose B is a projection of B onto the column space of Q, which is the same as the column space of A. The column space of A is the same as the column space of Q in the QR factorization process. And I have this little silliness here where W is the subspace spanned by the columns of A. Actually, I just called that the column space of A. So let me go ahead and erase that. That's not even needed in this discussion. Therefore, we have that A times X hat, which was Q times Q transpose B, is actually the projection of B onto the column space of A. And by definition, that means that X hat is a least squares solution of AX equals B. Because again, A times X hat is equal to the shadow of B onto the column space of A. Now, Theorem 14 shows us that this least squares solution is unique because the columns of A are linearly independent. So it's the only solution, and that proves this theorem. It's a lot to take in, but actually not such a terribly bad proof. Spend a while thinking about it, I challenge you. Anyhow, that's all I have for this video, and we are done with the least squares problems, at least the theory. In the future videos we're going to go into, we will deal with applications of least squares problems, or in other words, least squares models. I hope to see you there. Have a wonderful day. Be a great human being.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.